Hello to all, my name is Murat ÖZEN from Bursa Technical University from the Department of Chemistry. Today's topic will be about the synthesis and characterization of the Barium-Titanium-Peroxo-Hydroxide single-source precursor. Advanced ceramics are important materials in our daily lives, and advanced ceramics can be categorized under structural and functional ceramics. In brief, structural ceramics are materials which have very important mechanical and thermal applications, and functional ceramics are materials which have very important dielectric, ferroelectric, piezoelectric, and pyroelectric, and also ferroelectric properties, and also magnetic properties. Barium titanate is one of these functional ceramics with important dielectric, piezoelectric, and ferroelectric properties. Today's topic is not specifically about barium titanate, but instead about the precursor material for synthesizing barium titanate. Barium titanate, as I said, has very important electric properties which will depend on the temperature. Below 120 degrees Celsius, barium titanate is ferroelectric. Above 120 degrees Celsius, barium titanate is said to be pyroelectric. Advanced ceramics and the quality of advanced ceramics will depend on many factors, among which the precursor material is and the quality of the precursor material is an important one, because the precursor material when treated hydrothermally, for example, or solid state treated, such as in the molten salt synthesis method or the tape cast method, the quality of the precursor material will determine the final quality of the ceramic material. There are very different and various routes for synthesizing the precursor material for these advanced ceramics, such as the oxalate, alkoxide, and tartaric acid, and also the peroxide and hydrous routes. Many of these precursor routes contain organic compounds which will leave unwanted species after burning out the organic compound and will create pores in the final ceramic material. And also, depending on the precursor route chosen, some synthesis routes may produce secondary phases which will determine the final quality of the ceramic material. The precursor route chosen in this work for producing barium titanate was the peroxo-hydroxide route, which is described by the article from ÖZEN et al. Published in 2016, which was actually adapted and modified from a research article from Lee et al. Published in 2006. In brief, the synthesis route is as follows. Titanium tetrachloride is added to a barium aqueous solution with barium-titanium ratio of 2. Afterwards, hydrogen peroxide is added to this barium and titanium aqueous solution. The peroxide-titanium ratio was kept at 3. The solution was stirred for about 13 minutes. Afterwards, the solution was treated with ammonium hydroxide to about pH of 10, and the solution was then stirred for another 2 hours. After 2 hours, the solution was filtered to a Buchner filter, and the final barium-titanium-peroxo-hydroxide precursor material was obtained. According to literature, the pH of the solution will determine the nature of the titanium complex, and about a pH value of about 9 to 10, the titanium complex is said to be binuclear with peroxo groups between two titanium central ions and hydroxyl groups attached to the central titanium ions. But the exact nature of the complex is actually not defined. It is only suggested that the titanium complex is binuclear, and a definite answer was not given. There are, however, some literature available which describe titanium complexes which are actually oxalate and citrate titanium complexes, but the nature of the barium-titanium-peroxo-hydroxide precursor as described here is not given in the literature. The structure of the barium-titanium-peroxo-hydroxide precursor material as described before is said to be, or is thought to be, rather, to be binuclear in nature as described or as shown here, with peroxo groups between central titanium ions and an oxo bridging group, or an oxo bridging group between titanium ions and peroxo groups attached sideways to the central titanium ion, or even tetranuclear titanium complexes are also described in the literature. But as I said before, the exact nature of this particular precursor material is not defined. So the aim of this work was actually to analyze and to study the nature of this precursor material. For this, various synthesis parameters were studied, such as the barium source, stirring of the peroxide solution, the nature of the precipitating reagents such as sodium hydroxide, potassium hydroxide, ammonium hydroxide. The temperature of the solution was also varied between 20 degrees Celsius and 80 degrees Celsius, and the reaction time of the solution was also varied between 2 and 24 hours. Some results of these synthesis parameters are shown here. These are Raman and infrared results, but XRD and elemental analysis results were also performed. Instead of going through all of these results, which will be very exhaustive, I will be summarizing the main results here. The different characterization methods that were used, as I said, were Raman, infrared, XRD, and EPME analysis, which is an elemental analysis method. In Raman, we will be looking at specific peaks or band at above 800 centimeter minus 1 and around 600. In IR, we will be looking at at bands at about 800 centimeter minus 1 and about 600 centimeter minus 1. In XRD, we'll be looking at a broad band, and also if there are unwanted or secondary phases. For example, in this particular XRD diffractogram, we see the unwanted barium carbonate phase. But what we want is a very broad diffractogram, such as here, without the barium carbonate. And in the elemental analysis results, we'll be looking at a barium-titanium ratio of about 1. When we study all of the results, Raman, infrared, XRD, and EPME analysis results, we found that when we use barium chloride, when we stir the hydrogen peroxide solution for about 20 to 30 minutes, when we use the ammonium hydroxide solution as the precipitating reagent and adjust the pH of the solution to about 10, and use very low temperatures, room temperature and even lower, and the reaction time of about 2, which is actually more than sufficient, we obtain a high quality precursor material for barium titanate. An XRD result is shown here, which shows a very broad band and is typical of amorphous precursor materials. At least at the macro scale. At the nanoscale, the material might have some structure behind it, but all in all, we see that the precursor material that was obtained here is an amorphous material. The precursor material was also thermally analyzed by TGN-DSC. The TGN-DSC graph is shown here, and the Raman, infrared, and XRD results are shown here below. The Raman infrared and XRD results are of precursor materials which were treated at 400, 550, 650, 900, and 1000 degrees Celsius. When we analyze all of these results, we see that, first of all, the thermal analysis show that we have three main regions at about 25 to 250 degrees Celsius, which is the evaporation of molecular water, 250 to 525 degrees Celsius, which is the hydroxylation of hydroxyl groups, 525 to 825 degrees Celsius, which is the decomposition of peroxyl groups, and the crystallization of the precursor material into barium titanate. Raman infrared and XRD results support the crystallization at about 550 degrees Celsius. We see that here the peroxo band here and here disappear at 550, and the precursor material is transformed into barium titanate above 550 degrees Celsius. XRD results also show the same conclusion. We see that above 550 degrees Celsius, the material is transformed to a single phase barium titanate material, which is actually tetrachrome. The present work shows that the precursor material, titanate precursor material synthesized by the peroxo route, is actually a very high quality precursor material to synthesize crystalline barium titanate, and depending on the synthesis method, for example, when we use thermal treatment, the precursor material will be transformed to barium titanate at above 550 degrees Celsius. When we use a wet chemical method such as the hydrothermal method, the material will be transformed to barium titanate at even lower temperatures, for example 80 degrees Celsius and higher. Preliminary DFT calculations back up the notion that peroxo groups are sideways attached to titanium, and that there is at least one oxo bridging group between two central titanium ions. To further analyze the structure of the peroxide or the peroxo-hydroxide precursor material, in the future we intend to do detailed infrared and Raman study on the precursor material, and we also intend to systematically analyze the different titanium complexes which depend on the pH value of the solution. We also intend to isolate single crystals of the barium titanium peroxo-hydroxide material and to analyze it with infrared and Raman, and to do more DFT calculations and combine these calculations with Raman and infrared. And we hope then to definitely define the structure of the barium titanium peroxo-hydroxide complex. Finally, I would like to thank the Scientific Research Projects Fund at Bursa Technical University, the LATCA Group at University of Antwerp, MITAC, the Central Research Laboratory at Bursa Technical University, the editors and referees for their contribution, and the IOSense 21 conference for giving me the opportunity to present my work. Thank you and have a good day.